Okay, so let's dive into this really fascinating project. It's all about building a new kind of collective intelligence, one that doesn't just follow our instructions, but actually learns, adapts, and, get this, anticipates what we need, sometimes before we even know it ourselves.
And this quote, it just perfectly nails the whole idea. Imagine technology that feels less like a tool you have to command, and more like a partner that just gets it. It's a really powerful metaphor for a system that actively helps us navigate complexity.
Now, this isn't science fiction. This is a real, concrete design goal. And to understand how we could possibly build it, we first have to talk about a pretty fundamental problem with how our digital world is put together.
Yeah, it turns out our digital world is built on a surprisingly shaky foundation. And that foundation is what limits its ability to handle true, messy, real-world complexity.
So here's the problem. Almost all of our software is structured like a tree. You have a root, then branches, then leaves. Just think about a file system on your computer. It's a hierarchy, and while it's familiar, that rigid, top-down logic really struggles with the dynamic, interconnected way the real world actually works.
And the difference? Well, it's night and day. In a tree structure, you can't easily connect different branches. Information gets siloed, or you have to awkwardly duplicate it. But a graph-based approach? That lets you have flexible, direct connections. It represents relationships as they actually are, instead of trying to force everything into a strict hierarchy.
So, if trees are the problem, right, then we need a whole new language, one that's built on these direct connections. And the key principle behind that new language is something called compositionality.
And that brings us to this absolutely crucial idea, compositionality. You can think of it as the art of building big, predictable systems from small, simple Lego blocks. Each little piece has a clear way of connecting to others, so you can plug them together to build something much bigger, without causing all sorts of unexpected problems.
So what is this language that lets us do this? Well, it's a graphical one, and it's known as string diagrams. It's a totally visual syntax that gets us way beyond the limits of just text-based, tree-like code.
So instead of text in a tree, I want you to picture this. You've got processes that are like little boxes, and the flow of information between them are literally wires connecting them. It's this brilliant, much more intuitive way to model how systems work. You can actually see how things interact without any of the confusion of variable names or scopes.
And what's so cool about this graphical language is how incredibly expressive it is. It can model way more than just computation. It can represent abstract ideas. For instance, a concept like red or blue can be defined as a specific state in a conceptual space, turning something abstract into a tangible point in a geometric model. It's pretty wild.
Okay, so we've got a new language for describing systems, but now the system itself needs a brain, right? A way to think and learn and act. And this is where a really fascinating theory from neuroscience comes into play.
This is where we bring in active inference. At its heart, it's a model of how living things, including our own brains, figure out the world. See, we don't just passively take in information. We are constantly trying to predict it. And when what actually happens doesn't match our predictions, we feel a kind of surprise, and we act to reduce that surprise in the future.
It's this really elegant but powerful four-step loop. First, the system has a model of how it thinks the world works. Second, it observes what's actually happening. Third, it measures the difference, that prediction error or surprise. And finally, and this is the active part, it takes action to either make the world more like its predictions or it updates its own model to make better predictions next time. It's a constant cycle of learning.
Okay, but here's the thing. This isn't just some abstract theory. These two big ideas, string diagrams and active inference, are actually being used to build this new form of collective intelligence right now.
The project is called DuckGame, and its goal is to be a kind of super intelligent conductor for all sorts of collaborative work. It uses that compositional language of string diagrams to model workflows, and it uses the learning mechanism of active inference to adapt those workflows in real time.
And if you want to get a sense of just how ambitious this whole thing is, just look at the kinds of questions the project is asking itself. They range from the high-level mission all the way down to specific user pain points, and from big technical choices like Aptos versus Solana to deep governance issues like what would trigger a hard fork. This is a truly massive, holistic approach.
But here's the reality check. A system this powerful can't just live in its own little world. To be a true conductor of our collective work, it can't just replace everything we already use. No, it has to integrate with the tools and the AI agents that we rely on every single day.
For DuckGame to really work, it has to connect to everything.
But as you can see from this table, different AI tools like Claude and Copilot all have different capabilities. They don't all speak the same language. So the goal is to create a universal standard, and that's where the Model Context Protocol, or MCP, comes in. Think of it as a universal translator, allowing DuckGame to orchestrate this entire ecosystem of tools.
All right, so let's tie all of this together. We can now go back to that intelligent elevator we started with and see it not just as a cool metaphor, but as an actual blueprint.
So let's just quickly recap. We started with the problem of our brittle, tree-based systems. The solution we found is this DuckGame stack, a super flexible language with string diagrams, a learning brain with active inference, and universal connectivity through the MCP. You put those together, and they create the foundation for a totally new form of collective intelligence.
So that elevator without buttons, it's not just a metaphor anymore. It's a real, tangible vision. It represents tools that don't just sit there and wait for commands, but that actively learn from how we work, predict what we're going to need, and reconfigure themselves to help us reach our goals, all while minimizing the friction and surprise along the way.
And that really leaves us with this one final big question. Our tools today are powerful for sure, but they're passive. What happens if our technology could become an active, learning participant in our work, genuinely amplifying our collective intelligence? Just think about it. What would we choose to build together then?